Okay, let's take another look at thermal expansion and also thermal stress. So we have some train rails that are laid out. They're 12 meters long. So let's just kind of extract some information as we go along. So they're 12 meters long, is L naught, and they're placed end to end. They're laid on a winter day. Their temperature is -2 degrees Celsius. So this would be kind of like our initial temperature, I guess, would be -2 degrees Celsius. We need to know how much space has to be left between them if they're to just touch on a summer day when the temperature is 33 degrees Celsius. So our final temperature here is 33 degrees Celsius. And that's part A. And then part B is if they're mistakenly laid in contact with each other, what's the stress when it's 33 degrees Celsius? So, for part A, we're going to find kind of basically we can look at them if they're placed end to end. There's one here and there's another one here. It's going to they're going to stretch in both directions, right? Right, it's going to stretch this way and this way, really. But then this one's going to stretch this way and this way also. So really, we can just look at it kind of like stretching out just one direction, right? So we really just need to know the total delta L, and that's going to be how much we need to put in between, how much of a gap we need to leave in between, right? Whatever delta L is. So we're going to look, and for A, we're going to look for just delta L. And for part B, we're going to find out, what's the stress, so force over the area, if there's no gap, here, okay? So, we're told that these are steel rails, right? And so we actually have another piece of information. We have alpha for steel, which we can get from table 12.3 in the textbook. I'm sorry, 13.2 in the textbook. This is the same as what we used in the last exercise too, 12 times 10 to the -6 per degree Celsius, right? So we can, for part A, we just have delta L is equal to, L naught alpha delta T, right? This alpha is given in degrees Celsius. Delta T is going to be in degrees Celsius. We're good there. L naught was 12 meters. Alpha is 12 times 10 to the -6. And delta T is 33 minus -2. That's 35 degrees, right? So the change in length here, delta L, is equal to 0.005 meters or 5 millimeters. So we need to leave a 5 millimeter gap between the rails. Okay. If we don't leave a gap, then we want to find out, how much stress is going to be on these, and is it going to make the rails buckle or something and potentially cause a wreck, right? So for part B, we want to find the stress, the force over the area, which we said was Young's modulus times the coefficient of linear expansion times the change in temperature. Not change in length, but change in temperature, right? Okay, so we know alpha already. We need Young's modulus, right? So we can look this up way back from chapter 5. And Young's modulus for steel, this is equal to 2 times 10 to the 11th, right? Newtons per square meter, pascals, right? By the way, I'll give you all of these, if you need them on a quiz or exam or something, I will give you all of these constants here. So the stress, the force per area, as Young's modulus, 2 times 10 to the 11th, times the coefficient of linear expansion, which was 12 times 10 to the -6, alpha, and then times the change in temperature, which was 35 degrees Celsius, right? And so the stress we have here, force per area, this is equal to 8.4 times 10 to the 7th pascals. So pretty significant stress, really. 84 million pascals, 84 million newtons per square meter. It's a pretty significant stress there, something that we probably don't want these steel rails to have. And this is even considering, what happens if the railroad, it slams on its brakes and then it heats up the rails because of braking too. So probably good to leave a little bit of an expansion gap there if need be.